Hello there and welcome, students. We're going to be looking at exponential functions today. Exponential functions are those functions that have an x in the exponent. We've been looking at quadratics. Quadratics look something like an x squared, where the exponent is some number and the base is the variable. Now we're going to swap that around, and we're going to be looking at those functions that have a number as a base, and in the exponent we're going to have a variable. One of the best ways to look at new functions is to graph them. And we don't know what it looks like, so we're just going to plug in some points, find some dots, and see what it looks like. So I usually like to plug in, 0 and a few positive numbers, and then I also like to plug in some negatives. So let's look at these. This reads f of 0. So f of 0, meaning I plug in a 0 for x. So that's 2 to the 0. Well, 2 to the 0 is a 1. So I have the point 0, 1. Draw a dot. F of 1, that means 2 to the first power. So that's just going to be a 2. So I have the point 1, 2. And then I have 2 squared, which is 4. And then I have 2 to the third power. Now 2 to the third power is 2 times 2 times 2, which would be 8. So let's plot those points. 2, 4, 3, 8. Look at this thing. And if I put in a 4, let's just do that. 4, 2 to the fourth power. That would be a 16. Man, this thing gets big really fast. Look at it just shoot right up there. Let's see what happens in the negatives. 2 to the negative 1. 2 to the negative 1. That means 1 over 2 to the first, or negative 1 is 1/2. 2 to the negative 2 would then be 1 over 2 squared, which would be 1 over 4. So at 2, it's a fourth. At 2 to the negative 3, we have 1 over 8. Man, this gets really tiny. And at 2 to the negative 4, well, this would be like a 1/16. So this is going to keep on getting smaller and smaller and smaller. And if I connect these dots in the pattern that I think it's going to continue, I think it's just going to continue to get closer and closer to that x-axis without even touching it. And this is what 2 to the x looks like. So f of x, oops, let me make it so that you guys can actually see that. All right, there we have it. Now, let's see, for instance, what does f of x equal to 3x look like? Well, I'm just going to get my graphing calculator and start that out and see what that actually looks like. So let's pull that up here. All right, here I've plotted y equals 2 to the x in red. Looks just like our graph. I graphed y equals 3 to the x in blue, and now we see that graph. See how it's getting steeper and steeper, and if you'll notice, it gets steeper and steeper, and then as we come down here, it gets closer and closer to that x-axis faster. Let's see what happens to the 5x. So let me go here. Oops. Plug in my x here. X. Oh, look at that green line, how steep that got. And then what happens if I do y equals 10, raise it to the x? Oh my, that purple line is super duper steep. If you'll notice though, they all look exactly the same. That's just incredible, and it really doesn't matter which one I plug in here. They're all going to look the same. So that is absolutely fascinating. So my exponential functions, as long as I have a constant that's greater than 1, they all look just like this. And they all went through that point 0, 1. Another interesting feature of exponential functions, because anything to the 0 power is 1. Unless I'm talking about 0, of course. We're not even going to discuss that. Now I was looking at those functions that had a nice, beautiful base. I'm going to look at a function now that looks like maybe 1/2. Close parenthesis, raise it to the x, and see what that looks like. Oh my. Now let's look at this particular function. If I look at this one, this is 1/2 raised to the x. Instead of it going straight up along this way, you'll notice that it flip-flops it. It makes it reflect about the y-axis. I could have also asked it to graph, let's say 2, raise it to the negative x, and see what I get for that. Now, if you'll notice, it graphed it right on top of that other function. These two are identical because a negative exponent means 1 over. So what that really means is 1 over 2 to the x, which is exactly what 1/2 x is. We call these functions decay functions because they're getting smaller and smaller. They're dying functions. When I was looking at y equals 2 to the x, these are growth functions because they are getting bigger and bigger. But notice how they just reflect about that y-axis. So what kinds of questions would x, y, z ask you? Well, they're going to ask you some questions, mainly dealing with function notation, and see if you can plug these things in. So for number 1, we have that g of x equals 1/2 raised to the x, and we have that f of x equals 3 to the x. So number 1, they might ask you to find g of 0. That means you go to g, and wherever there's an x, you put a 0. 1/2 raised to the 0. Well, that would be a 1. Anything to the 0 power is a 1. Number 2, f of 0. So I go to find my f, and I say 3. Wherever there's an x, I put a 0. This would also be 1. Well, they made this easy, didn't they? Number 3, g of negative 1. So what I do here is I'll plug in my negative 1 for x. Negative exponent means to flip that thing. So that would be 2 over 1 raised to the 1. I flipped it, so I've taken care of my negative, and this would just be a 2. Here's another example of something they might ask you to do. This one is best taken in little pieces. They want you to write down whatever your f of x is. So I'm going to write that down. That's just 3 to the x. I wrote down f of x minus, they want you to write down your f, which is 3 raised to the x, but in place of x, you're going to write a 2. And then I just write down x minus 2 because there's nothing to do with that. And then this would then equal 3 to the x minus 9 over x minus 2. And that would be your final answer. Strange looking one, isn't it? When I start playing with exponential functions, I start finding that there is this special little number called e. And there he is right there, that e to the x. And this e is just a number. In fact, he's just about 2.7183, somewhere around in there, but he keeps on going. He's irrational. He is a lot like pi. So both pi, which is 3.14, and you know that if you deal with a circle, you're going to have a pi in there somewhere. Likewise, when I'm playing with exponential functions, you will often find this e, and this e is a number. And that's all he is. He's just like pi, where pi is about 3.14. E is about 2.7183. But it does keep on going. So let's look at that on a calculator. So here we are. I'm just going to push the E button up. And look, there it gives us this value of 2.71, and it just keeps on going. You'll notice here on this button, I have an e to the x because often, me get rid of that. Because often your e is being raised to some number, and let's just square it. And you'll see that they have squared the number 2.71. But don't be afraid of that e. He is just a number. I might as well graph that e because you are going to have to graph him. So let's look at y equals e, raise it to the x. Well, look at there. Looks just like all the others because, after all, e is 2.718 blah, blah, blah. You can even notice that y equals 2, raise it to the x. So you can see the red line, which is 2 to the x, is underneath because that 2 is less than. And if I asked it to graph y equals 3 raised to the x, you'd see that that e to the x is in between the red and the blue line because, and he's closer to the 3, because this red line is 2 to the x, this blue line is 3 to the x, and 2.71 is closer to 3 than it is to 2, isn't it? So XYZ is going to ask you to punch some buttons for e to the x. So take some time to find your e to the x on your calculator and use those buttons. A number of your problems will involve half-life. When you have a problem that involves half-life, what you will do is you'll be using a formula that looks like your amount at whatever time is given by your original amount, that's what that A naught is, times, and because it's half-life, this is a 2 minus T over whatever that half-life is, and a lot of times they'll use a K there. They don't really specify, but we're just going to write down that this is the half-life amount. Okay, so for our particular problem, in example 2, a patient is administered 1,200 micrograms of iodine 131. So 1,200 is our original amount. And how much iodine 131 will be in the patient's system after 10 days? Well, they tell us up here that the half-life of this particular isotope is 8 days. So I put negative T over 8 there. And then they want to know after 10 days, so let's just do A of 10, and we're going to do after 16 days, so A of 16. This is just a calculator exercise. Make sure that you can plug this into your calculator. So this would be, we're going to put in a 16 here over 8, and for that one right there, I'm supposed to put in what they say it was 10. So let me get that out of there and put in my 10. Punch the buttons on your calculator and you will get that these things, and then they'll tell you how to round them as well. So when they tell you how to round those and you punch that in, you should get about 504.5 micrograms for this one, and you should get about 300 micrograms for this one. If you have any trouble punching these buttons, be sure and send me an email and I can do some calculator work with you. Remember that your half-life amount goes right here in this little spot, and you have it 2 here because that's telling you that that's how that is decaying. Notice how it's a negative, so we know that the negative sign means that it is a dying or decaying function. Another application problem that they might give you is a compound interest problem. If you're dealing with money and it's a compound interest problem, this is going to be the formula that you're going to be looking at, where P is your principal or your original amount, and then R is your rate. Now they'll give it to you as a percentage, but this must be in a decimal form to input it into this formula. So be sure that you do that. N is your number of compoundings. So if it's an annual compounding, that would be a 1. If it's a monthly compounding, N would be 12. If it's quarterly, N would be 4. And T is your time. And this would be in the number of years. So let's look at this example. Suppose we borrow $500 from an account with an annual interest of 8% compounded quarterly. Find how much money we have after T years, or owed after T years. So amount after 5 years is going to be, our principal is 500. 1 plus our rate is 8%. Change that to a decimal, 0.08 over, and this is compounded quarterly, so N is 4. And then 4 times my time, which is 5. Be sure when you do things in the exponent, be very careful. Make sure you have a good number of parentheses to demonstrate that it is totally in the exponent there. If you crunch these numbers in your calculator, you should get $742.97. All right, the next one, there's a way to solve this using logarithms, but you can't really do that quite yet because we don't know what a logarithm is. We haven't covered those. And if you have covered logs, go ahead and solve this one using logs. But since we don't know about that, we're going to have to use a calculator. So our B question, and you will do this on some of your homework, which is why I'm covering this, we will get our graphing calculator up. So get your calculators. All right, we plug this in our calculator, but now we've got to go find the graph. For your TI calculators, you can just hit zoom and out and help find it, or you can hit window and adjust your window. Now, adjusting your windows is a very important skill to have. So it would be really nice if you were to just ask me how to adjust a window. I'm going to adjust this window on Desmos. All right, I'm going to show you how I'm going to do this on Desmos because your calculator is a lot like that. My X minimum, I'm going to make that a 0 because I just want to start it at 0. I don't like 0. Let's do -100. No, because we're just doing a few years, aren't we? We'll just do -1. And we'll make this be like 10. And we'll step size it by 1. The Y, my minimum value on Y, I want to be, let's say I want it to be 100. Ooh, I don't want that in there. And we'll make it go up to 1,000, and we'll step it by 100 and see what that looks like. Okay, so that's pretty good. That's pretty good. I kind of like that. So let's go back here and see what we have. So I've plugged in my equation, and then they wanted to know how many years till we reach $1,000. So I think I should have made this go on up to 1,500. I'm going to do that. Okay. So I also need to plot y equals 1,000, and then I can use the trace feature on my calculator to see exactly when that is. And here it tells me it is 8.751. Can you guys see it? Nope, you cannot. So I'll move this over. So I use the trace feature, and it says 8.751. And you do that same exact thing with your calculator, and you would just write that number in. All right, and that is how we're going to work these problems. Now, if you have any trouble, you be sure and shoot me an email, and I'll be glad to help you with that. Thank you, and y'all have a wonderful day.